All right, welcome back to operating systems. So lab 1 and /0, I actually hit the button now so you can actually see your grades. They were available before, but I forgot Quarkus has like a 3-step process to like unhide your grades. So hopefully you have those now. Most of you got 100. So lab 1 is probably too easy. So lab 2 is posted, so that's a bit harder. So lab 2 is split off into another harder section that's worth 20% where you get to become a sub-reaper for an additional 20%. So if you don't want to do that, it's worth 80. If you do, then yeah, you get that extra 100. So let's have some more practice today with processes. So also based off the lab 0 feedback, a lot of you are very ambitious and want to write your own operating system. Unfortunately, that is not where this course is aimed at, but where this course is aimed at, there is a teaching operating system written that's used for MIT graduate courses that at the end of this course, you can completely read and understand everything that's going on with it. So it's pretty basic. You'll actually learn everything behind it. The goal of this course is to help everyone be a better programmer, not those that just want to do operating systems. So the goal of this course, you should be able to read this, but you should be able to write better programs at the end of this course. So we're more at the system call layer. This is like a lot of kernel code. It's a full operating system. You can read it. There's instructions in the repository if you want to run it in the VM. So it will also run as a VM. So it will run as a VM in your VM. So like there's VM inception if you want to write it. And it's basically a re-implementation of Unix v6, which is really, really old, but it's still a functional thing. And it's done in C. And the minimal assembly it has to do is all done in RISC-V. So if we go ahead and we could read some of it if we want. So like for instance, this is the Init process from that. So this is what they compiled to create Init. And we should be able to read it all. There's just some magic. So they open a file called console, which is a magical file that represents a serial console that you can read and write bytes to. So you probably, hopefully, maybe have done that in computer organization where there's some magical memory address you could write a byte to and read a byte from, and it would communicate over a wire or something like that. So that's what this terminal would represent, or this console would represent. And then what it does is it duplicates that file descriptor that it opens twice. So dupe just copies that file descriptor and creates a new file descriptor. So this would create a file descriptor 1 that points to that same console. This would create file descriptor 2 that points to that same console. So now this process has file descriptors 0, 1, and 2. Because it's init, that convention of having those open doesn't exist because you're init, you have nothing, you have to start that convention. So it starts the convention, and then it has a for loop here that prints off what it's doing. Remember, one of the responsibilities of init is it has to create other processes. So this one, it's a very dumb init. It will only start a shell. So it says printf init starting shell, then forks, and then it checks if there's an error. If there's an error, it bails out and your operating system doesn't exist. Otherwise, it checks if it is the child process. It execs sh, which is the same thing as our exec ve. So it tries to replace the child process, load that sh program, and start executing that. So if it's successful, the child process gets transformed into sh. Otherwise, they know there's an error, so they're just going to print off it failed, and then bail out, and it's dead, and then your program or your operating system's dead. Otherwise, they have this for loop that says that's just wait, and before we had a pointer to keep track of our W status. They don't care about reading the exit status, so they just pass a null pointer in there so it won't update anything. But they just call essentially while true wait. The only exception here is that they check if the process that just terminated is equal to the shell I created. Well, then it wants to restart this shell. So we'll break out of this and then create a new process and launch and exec sh again. Otherwise, if it returns an error, it bails out. And then otherwise, it was a parentless process. We just cleaned it up. It was a zombie. So we just cleaned it up, not a zombie, got rid of it, all good, and that's literally all Init does in this operating system. So, like I said, doesn't have to be that complicated. This is what Init does. So, with that detour, we can talk about old operating systems since we're on that topic. So, for old DOS, if you've ever heard of DOS, you guys are probably way too young to ever hear of DOS, but that was back in the day when CPUs were like a megahertz at best and couldn't really do much. So there was this old style programming called uniprogramming, and that meant only one process ran at any one given time. You can imagine how boring life was back then. So you could only do one thing at a time. So if you wanted to play a game, you launch your game, you couldn't do anything else until you're done with your game, and then you could open your word processor or something after you close your game. So alt-tabbing when your boss comes in doesn't work. So that was the system back in the day. Very, very simple. You don't have to do any special scheduling or anything like that. Process runs, you let it run till it's done, you run the next process. So multi-programming is what we have today. You can have multiple processes and they can run in parallel or concurrently, which if you just understand English, you're like, what the hell? Those are the same words. Why do you say or? Once we get into threads, we will figure out that computer scientists like to overload words, so those two things actually mean slightly different concepts. So we'll get into that when we get into threads. But most operating systems, they want to run everything in parallel, concurrently, use all your CPU cores, go as fast as possible, use your hardware to its maximum capability. So once you have multiple processes, you have to decide what to run at any given time, and that is the job of the scheduler that we'll be going through for the next few lectures. So remember, when we create a process and we load a new one, the operating system at least has to load it into memory. Then it gets put into that waiting state, and then the scheduler, which we'll see in the next two lectures, decides when it gets to run. But first, we have to focus in on the mechanics of actually switching processes that we've kind of touched on before. So the core scheduling loop is going to look something like this. It's going to pause the current running process and then save its state so you can restore it later. That would save all of its registers, right? Because we're representing each process as having its own virtual registers, so its state would at least include the registers that it currently has. Then we would ask the scheduler, what is the next process we're supposed to run? Again, we'll answer that question later. Then after that, we load the next process's state and then let that run. So we would just do the reverse of saving the state. We would essentially set all the register values. Yep.
We're assuming two processes run at the same time, right?
So this is on a single CPU core that can only run one thing at a time. But you could have multiple CPU cores running different processes.
Interesting.
But yeah, this is just for a single core. This is what would be happening on a single core. So also, once you have multiple processes, you can schedule them in different ways. So one ill-advised way is to let them kind of schedule themselves, and that is called cooperative multitasking. So a process uses a system call to tell the operating system explicitly, okay, you can pause me now if you want to run another process. Well, that's probably a bad idea in general, because if someone just wrote a program that never did that system call, it kind of goes back to that old uniprogramming way where that program would just run until it's done, and the operating system would have no control over it. So you might hear this term. Basically, that's only possible if you are writing every single program on your machine and you want to be very precise about when things switch. You could do something like cooperative multitasking on like very small embedded machines or things you have control over. But in general, operating systems need to do something called true multitasking, where the operating system or the kernel maintains control and pauses processes. You don't get a say about it. So for true multitasking, there's two different ways it could do it. The kernel could give each process a certain time slice and then just give you the CPU for that amount of time. Once your time is done, then it can switch to a different process. Another thing it can do, which is what pretty much everyone actually does, is you can wake up periodically using interrupts to do scheduling. So if you're in kernel mode and you have control over the CPU, you can set a timer interrupt, and you can say, hey, CPU, after, I don't know, like 100 milliseconds, please send an interrupt to me so I, the kernel, can handle it. And in part of handling it, I will pause that process and take the CPU away from it. So that's the way kernels actually do it. They just set a timer interrupt, they get control back, and your process doesn't get any say in the matter. So that mechanic of like saving a state and loading a state, that swapping process is called context switching. You're going to have to know that term for this course. We'll probably say it all the time. So at minimum, as part of a context switch, we have to save all the current registers, and we're saving all the same values using the same CPU we're trying to save them on. So we have to save them to memory, which is going to be, of course, fairly slow. And also on some CPUs, on like modern x86 CPUs, the number of registers you have is like insane. So there's special registers for floats, there's special registers for vector instructions. There's so many registers on your actual machine, whether or not you know about them. So sometimes that is slow if you just save literally every single register on your machine. If it's a very complicated CPU, that could be really slow. So because that's really slow and your program might not actually use it, you don't really want to save everything. So if the kernel can keep track of your process and say, for example, your process never uses floats, so it never uses any float registers, well then that software can be smart and be like, okay, this process doesn't use floats. I'm not going to save the registers because they don't use them. It doesn't matter. So why would it do something like that? Well, context switching is pure overhead. And what does overhead mean? It means your kernel or operating system is not doing something you would like it to do. So it's just wasting time. Any time you spend just physically saving some state and loading some state, that is time that is not spent running applications, which is all you really want your operating system to do, is just run applications. So the longer the context switch waits, the more unhappy you will be because your hardware will be wasted, right? If it spends like 50% of its time just saving state and not running your program, then you're going to be fairly mad and probably switch operating systems. Want to be as fast as possible. Typically, I mean, like 99% of the time, your kernel should be just executing applications. So kernel needs to be, really good kernel needs to be smart, save as little as possible without destroying anything. So now we can get into some more fun IPC stuff. So we're going to learn another IPC mechanism called a pipe. We saw that before when I showed you that bar character. Well, that is actually a system call, and it's actually called pipe. So it looks like this. The system call takes as an argument an integer array of 2 ints and just returns an int, and it only returns whether or not it failed. So if pipe returns -1, it means it failed. It sets error no. It does something we all know it does. And if it returns 0, it means it was a success, and it is going to write values to this array. What values is it going to write? Well, that pipe's going to represent a two-way communication channel, and you will get 2 file descriptors. So in that array, the file descriptor at index 0 is going to represent the read end of the pipe, which means you are allowed to do read system calls on that end of on that file descriptor. The file descriptor at index 1 is the write end of the pipe, and you are allowed to write data to that end of the pipe through that file descriptor. And the rule is, whatever you write to the right end of the pipe, if you try and read it, you'll read it from the read end of the pipe. So you might think that's a bit weird, but you can think of it as a kernel managed buffer, and we'll see that that's actually useful for IPC. Yep.
Sorry, what's a file descriptor again, and why does it have like an int and instead of anything relative to a pointer?
So a file descriptor is just a number, and the kernel uses it to represent something that you can read and write bytes to.
Then
Right.
how do we know like what is a file descriptor for a file that I want to read or write it to?
So you know what file descriptors, because like open returns a file descriptor and it just returns a number that represents what file descriptor that is.
Oh.
Right. Right, you used it in lab 1. Yep.
What is the process like deciding which files are being used as how is the process actually determine which file the process uses as this pipe?
So for this pipe, so the question's how does the process determine what file descriptors it's using? So by default, we have the like 0, 1, and 2, and you're expecting those to always be open. And aside from that, the valid file descriptors are whatever you create. So you can create it through an open system called open an actual file, like a real file, or through this pipe, which doesn't represent a real file, but things we can read and write bytes from, right? So, but you control them, and your file descriptors are independent of the process. And we'll actually use this and see that, because yeah, it might not be obvious just by me saying it. Doing is always better. All right, so yep.
Is there any particular reason it takes an array of 2 ints as an argument, or I guess a pointer, rather than 2 int pointer arguments?
Yeah, question is why does it just take a array instead of just 2 individual int pointer arguments? And that's because that would take 2 arguments. This is 1. This is clearly more efficient, right? Yeah, they could have done that. It doesn't really matter. They just decided to do this because they thought it was easier. But yeah, yours would probably be more flexible if you didn't want them beside each other for whatever reason. All right, so quick, another aside. So using that ampersand in your shell, we can actually explain that now. So if you use ampersand at the end of your command, your shell starts that process in the background and returns immediately. So it just creates a child process, and then it gets reparented because the parent immediately dies. Or sorry, it doesn't get reparented. So it just starts it in the background and as a child of your shell, and just lets it run until it's done, and it will tell you whenever it's done kind of asynchronously. So it will output the PID whenever you create it and let you know when it's actually finished. So with that, and this character will create a pipe between 2 processes we saw before, so we can actually explain this fun fork bomb. Remember that was like while true fork. So this is a valid, you can apparently name bash functions a colon. So this defines a function called colon, taking no arguments, and what it does is call colon, pipes it to another colon, just to glue 2 processes together, and then does an ampersand to run that in the background. So every time this comes through, it creates 2 processes. So this ends the definition, and then it calls colon once. So each of these will create 2 processes, and then create it, and then we'll get that exponential explosion, and you'll probably have to reboot your system. So do not run this command. Yep. So a colon is the name of the function we're defining. So we define a function called colon. And why? Because if you give this to 4th year, if you call it fork bomb or something like that, they might not run it. But if you just call it colon, this looks kind of like, it might be fun to run this, right? Yeah.
Can we try?
No.
So the first colon, inside the parentheses,
Yeah.
it's piping the output of the first colon into the second colon.
Yeah.
So
But they're not going to generate any input.
So is it just like a null output that it's inputting from the first colon into the second colon because it's
Yeah.
not returning anything?
Yeah.
Okay.
Yeah. It's just a way to glue them together so that this ampersand it launches 2 processes. So every time I call this, I launch 2 processes. Yeah.
So repeatedly calling itself?
Yeah, so this is basically while true fork. So this is while true fork, but it's like insanely difficult to read. And you can probably not to say you should do this, but you could trick, if I gave this to you while you were taking 105 and told you to run this, you'd probably do it, right? depends how much some of you trust me. Maybe you would never trust me anymore after this course, but you might before you known me. All right, let's just see so let's see the pipe example first, because that'll be like the whole lecture. Yep.
Oh, have you ever actually seen that video? Like, have you ever actually seen the effect of that?
Have I seen the effect of that?
Like, yeah, like, have you ever seen if the kernel is smart enough to, like, stop not from running after a while? Or do you think the kernel is not smart enough to realize that it's affected by
Yeah, so that's a configurable thing. Your kernel is smart enough to detect that, depending on how new it is and your security, whatever you have. So if you try, do not run this on any university computers, but they're smart enough to know things like this will happen. They'll probably limit you to like not that many processes, which is one of the reasons we're using a virtual machine, because we can break it, we don't really care. Like if you run this and you go, oh crap, you don't have to physically restart your machine like you guys made me do. You can just restart your virtual machine, right? No harm, no foul. So that's why we like virtual machines in this course. Yeah. The fork bomb. Yeah, so the last colon there just says, like, if this was called fork bomb, this would just be called fork bomb. It just runs it once, right? So this sets it off. So this defines the function, and then this calls the function. Yeah.
Oh, so if it was called fork bomb, would the version size also be called fork bomb?
Yeah. Yeah, so if I rename this to fork bomb, I would have to rename these to fork bombs, and then it's really long too. And if you see fork bomb like 4 times, you probably wouldn't run it. If you see 4 colons, Some of you might, yeah, most people don't know that colon's a valid function name for whatever reason. All right, but let's go into the fun fork example we can break our brains with today. So, here is our main. We're going to declare an integer array of 2 ints called FDs. Then we will call pipe. Now I wrap everything in this check function. What does this check function do? Just make sure that it returns something other than -1. If it returns -1, it means there's an error. So I'm just going to have some error handling code here because I don't want to write this like 10,000 times. So whenever you see check, I'm just checking for an error code. We'll just assume everything works. So I call pipe. So what that will do, if it is successful, and I will assume it is, it will create 2 file descriptors. So we'll have FDs at index 0, and then FDs at index 1. So because this will create 2 new file descriptors, and we know 0, 1, and 2 are already open, we can probably argue about what the actual number will be because we know how the kernel works. So what number file descriptor will this be? Likely 3, and this represents the read end of the pipe. This one would probably be file descriptor 4, and it is the right end of the pipe. So, right after we create it, we fork. So we create a new process. It is a complete clone at the time of the fork. So at the time of the fork, this process has 5 file descriptors open. 0, 1, 2, 3, 4, 5. Or sorry, 0, 1, stops at 4. So the child process is also going to have all those file descriptors open. So you can think of the file descriptors as just a number. The kernel knows what they actually point to, but the kernel kind of treats them like pointers. So for both processes have file descriptor 4, and that's independent for each process. But in each process, file descriptor 4 points to the same thing. So they both point to the right end of the pipe. So what do? Let's see that we can actually transfer some data between these 2 processes. So we check the PID. If it is greater than 0, we are the OG parent. So we just declare a string called howdy child. I don't know why I'm Texan today, but I am. Take its string length, and then we will write to FDs1, which is the right end of the pipe. And we'll just give it the address that starts the string, tell it to write the length of the string, and then we will check for an error. After the parent's done, it would close both file descriptors, return 0. Returning from main is the same as calling exit. So if you want, this could be exit 0 if it makes it easier for you to read. Otherwise, if we are the child process, we declare a character buffer of this magical size. We do a read system call from the read end of the pipe, give it the buffer, say the maximum size we have, number of bytes read, and then we will just print off the message we receive from it. So if I go ahead and compile this, I'm in the wrong directory. I'm in that one. Whoops. Okay, so if I run that, I get child read. Howdy child. So that came from the child, and the child, that just read. It didn't write or anything. That string just magically came from the parent. So the parent wrote that string to the pipe. You can think of it as just being a buffer that's managed, like memory that's managed by the kernel, that it protects and makes safe, so you can only access it through a pipe. So that would be managed by the kernel, and then the other process comes back, reads from that pipe, and then it reads whatever the other process wrote to it. So it's communicating across processes. Cool. Any questions about that? Yep.
So then are there two files where one is for read and then the other is for write, and then it kind of transfer data between the two files?
So yeah, there's a question, do I have two files then? So the name file descriptor is unfortunate because they don't actually represent files. So remember, file descriptors just represent something you can read and write bytes to through system calls. They don't necessarily represent files. They can, but it's not necessary. In this case, this doesn't represent a real file. So a pipe is basically just some memory managed by the kernel. So that fulfills like what I can do with a file descriptor because I can read information to it, and then the other one can read information from it. But yeah, that's a good question, but just because they're called file descriptors doesn't mean they're files. All right, any other questions? Yep.
Doesn't each process have like virtual memory? So how come like the memory that's written by one process can be read by another process?
Yeah, so that's a question. So the question is, if they have virtual memory, how can one read the other? So remember, these processes are completely independent. Just their file descriptors point to certain things. And that memory, when I write in this process, howdy child, it doesn't actually exist in, it does exist in this process's memory, but after it writes it to the kernel, and then the kernel's managing that information. So after it writes, the kernel copies that memory and puts it somewhere in a safe kernel space, in some kernel memory, so that another process can access it. So they're still independent, but I wrote that information to the kernel, and it can do magical stuff with it. So I wrote howdy child to that, and then if I modified it after the write call, I mean, the child process would never see it because that would be in my virtual memory. But if I write it to the kernel, and then it's written to the kernel gets to manage it, and then in the other process, I read it, then it reads it into that process's memory. Yep.
Okay, so pipes are one way, but could the child print to the parent? Same thing, but instead of this being run by the parent, run by the child?
Yeah, so the question is, can I just do it the other way, right? If I just have a write in the child and a read in the parent? Yeah, so if you had it the other way, that also works. That's fine.
So then what makes it one way?
So what makes it one way is that whatever I write to it, pops up in the read. I can't write to the other end of the pipe, so I can't write anything to FDs at index 0. So that way they're communicating one way with each other. If I wanted one process to send information to another process and then that to send it back, like simultaneously, I need 2 pipes. So I could switch it where like one writes and the other reads all the time, but I can't intermix them together without having 2 pipes.
Or, I mean, you could theoretically have one write and then read, and the other read and then write.
Yeah, I could have one read, then write, then read, but then I'm like, yeah, it's just kind of weird.
They can only send messages in one direction at a time, but they can send it in either direction because they both have access to both ends of the pipe.
Yeah, that's true. They can only send messages in one direction at a time. Yeah. But if you had some protocol and you only sent messages in one way at a time, you could do that. But in general, you just make 2 pipes. And then you don't have to worry about like making sure you're reading when you should be and writing when you should be. Yep.
How did you make sure that the write operation is before the data?
That's a good question. So how did I make sure the write happened before the read? Anyone tell me, did I have to do that? So I argued,
Why don't you have to do that, though?
huh?
Why don't you have to do that?
Yeah. Anyone, why don't I have to do that?
The read blocks until the write.
Yeah, the read blocks.
So basically, if you didn't write anything, you can't read anything.
Yep.
Interesting. Thank you.
Yeah, so here, if the child happens to execute first, before the parent writes anything, it would hit this read and reads a blocking system call. So the kernel knows that, hey, this read represents a read of a pipe. Someone could write data to it. No one has written to it yet. I'm going to wait and only return from this read whenever someone has written data from it. So this process will just go to Betty bye time, go to sleep, and wait for another process to call write. So this would go to sleep, state would get saved, and then the kernel would decide another process to run, even on a single CPU. And then it would be like, oh yeah, I should probably run this process. There's probably nothing else to do. It would eventually call write, and then it calls write, and then the other one can return from read. Yep.
Like maybe something like the FDS1 and 0, they are just like 2 integers. Like why couldn't we like just switch them and use the both rows?
Why couldn't we switch them? Oh, sorry, I deleted. Wait, so what do you mean by switch them?
I mean like, these are just 2 integers, so we can change the file descriptor. So
Ye-
in theory, I can write in FDS1, FDS0 and read in FDS1.
So they're just 2 integers, right? But they are 2 integers that mean something very specific if you talk to the kernel about them. So if I tried to do a write of FD's 0, which is file descriptor 3, the kernel is going to give us an error that's like, you can't write to a read-only file descriptor. So the kernel manages it. So because they're just integers, right, you could make them up too if you want. Like I could try and write to file descriptor 10, but the kernel manages that. It knows 10 doesn't mean anything. All right. Okay. Oh, yep.
So does that mean that we cannot write twice?
So the question is, does that mean I can't write twice for a pipe? And you can write as many times as you want to a pipe. In this case, the child process wouldn't see it because it only returns from read once. But in general, if you wrote an application that was like communicating constantly, it would have to constantly call read over and over again.
So in that case, the timing of read is actually because otherwise you will fetch the previous write.
Yeah, but usually you just call read and get all the data that's available for it. Yeah.
So first of all, can you slow down a little bit? Yeah, maybe a really stupid question, but like, if the parent, after the parent finishes writing, let's say,
Yep.
and if they close the file descriptor 0 and 1, isn't this kind of thing that it kind of closed the pipe? So in this case, how is the child gonna be able to read it?
Yeah, so that is another good question. So the question is, well, if the parent goes through before the child does anything and it closes these file descriptors, won't that mess up the child? Anyone else answer that one? Yeah, so remember all the processes are independent. So in the parent, both the parent and the child have like file descriptor 3 and 4 open, and they point to the same thing. So in the parent, file descriptor 3 points to the right end of the pipe, to the kernel, and to the kernel, the child, its file descriptor 3 also points to that same read end of the pipe. So if I close file descriptor 3 in the parent, it only closes file descriptor 3 for that process, not the other one.
So can we think about the pipe is like, for example, the read end, they have multiple ports. They have like 3 is one of them, the 3 in the parent is one of them, and the 3 in the child is another one. If I close the 3 for the parent, the child can still be able to read, right?
Yeah,
Okay.
yeah,
It's like you're talking in a private message and one side goes offline.
yeah. In fact, let's break something. Yeah. Well,
I was just gonna ask then, what does close actually do? Does it like free memory in like to the?
so it closed is the kernel saying that you are done with that file descriptor. You don't need it anymore. So that means if you close a file descriptor, like you can't access that anymore. You can't read to that. You can't write to it or anything like that. Right, we'll see why that's important in a second. So let's see. Well, people have asked some good questions. So what happens, I'll ask you a question. What happens if I do that? So I commented out the right in the parent. For full marks, who wants to tell me everything that is going on here?
Would be blocked forever.
Okay, something's blocked forever, yeah, uh-huh.
I was gonna say the parent would complete, or it doesn't matter which order, but yeah, when you get to the child process, then the read would just block forever.
Yeah.
Because nothing's coming.
Okay, and for full points, what is that child process?
What?
Oh, I heard a magic word. So, an orphan, right? So the parent goes away, the child is going to be stuck on this read call, and then its parent goes away. What happens to it?
It becomes an orphan.
Becomes an orphan. Where do orphans go?
Killed.
No. They go to the Reaper, which is init, which is process ID 1. So, if I go ahead and compile this and run it, I should have created an orphan, right?
Yeah.
How do I check if I created an orphan? PS. What about if I just wanted the process ID of whatever this is called? Here, there's pit of pipes. So you could actually write this now after doing lab 1, right? All it does is take a name and then prints off, like looks in proc, sees any processes that match that name and output their process ID. You could write this now. So I see that, hey, process ID, this is still running. That is called pipes. If I go ahead and, whoops, not you. If I go ahead and look at it, well, it's my process. It's sleeping. Its parent process ID is 1, so it did get sent to init. This is kind of chilling there. How do I get rid of it?
Kill.
Kill.
-9.
-9. Someone woke up and chose violence today. Yikes. So I could just normal kill it and it should work because I didn't ignore it or do something bad. But I could have killed -9 it if I really hated it. So that's fun. So what if instead, so let's really get our file descriptor knowledge here. So remember what I said about file descriptors, where like you should close them if you're not going to use them anymore. So in the child, well, when the child starts executing, it has the right end of the pipe open, right? So does the child ever use the right end of the pipe? FD1. Yeah, does the child? Yeah, does the child ever use it? No. What should I do when I'm not going to use it? Close it. Close FD's 1. And then after I do my write, I can go ahead and close FD's 0. So if I go ahead and I program correctly, we're going to notice something magical. Whoops. So if I run pipes again, whoops, whoops, sorry. I'll keep this commented out. So the parent isn't writing anything. Notice something magical. The child has returned. It's not running. Well, it printed this child read line, so what must have happened?
It reads no bytes.
Yeah, it read no bytes. So if read returns 0, that means what? End of file, or in more generic terms, it means it's not possible to get any more input. So the kernel is very smart. So the kernel knows, it keeps track of all the file descriptors for all the processes. So the kernel is very smart, and if no process has the right end of the pipe open, it knows it is not possible for any data to go into that pipe. So if it's not possible for any data to go into that pipe and you have read it all already, that's the same thing as end of file or no more output is possible. So in this case, it's not going to sit and read indefinitely because eventually the parent is going to close the right end of the pipe, and in the child, before I call read, I close the right end of the pipe. So when read returns, there is no right end of the pipe open, and I am free. I get an end of file character or no more input possible. I read nothing, I close, I do not create an orphan, I do things properly. Any questions about that? Yep.
Small point of you mentioned like two processes of having read through different descriptors.
Yeah.
You say it's like the same thing, but if process 1 close, it will disable that number that I see like 3. Well, the kernel reads 3 and says it's invalid, and another process will say like, okay, 3 is invalid, I can't close it.
No, so file descriptors are just valid for a process. So they're independent in a process, and whatever they represent, they might represent the same thing as another process.
So we can do the same number and they will be
Yeah, so in this case, right after the fork, both processes have all the file descriptors open. So the child has file descriptor 3, and so is the parent in this case. Right, they all have file descriptors open. Yep.
In the first case, well, before we close both file descriptors, it's just reading forever, right?
Yeah.
Will the operating system ever see that it's going to sleep forever and kill it, or will it just let it sleep forever if we just left it there and didn't kill it?
So yeah, the question is, well, when it slept forever, so it would sleep forever in this case. So if it slept forever, can't the operating system be smart enough to know it will sleep forever? So because the only process that has the right end of the pipe is the process that is currently reading, right? So you might think it is impossible for it to somehow write data. Not true. So even though it is doing a write, what happens if I send a signal to it? It does whatever the handler does, right? If I wrote a silly handler, I could technically write a handler that wrote to the right end of the pipe. And because that is technically possible, although otherwise insane, the kernel has to be super conservative and say, because that is a possibility, there's no way I can tell with 100% certainty that will never happen, then I can't just end it. I have to let it read because maybe in 100 years that happens or something like that, right? So the kernel has to make sure that it does things correct. So even if there's a 0.1% chance that something weird will happen, it has to account for that, which is why this course has a bunch of edge cases like that, right? You would clearly expect that you looking at this program can probably analyze and be like, that's not even possible, but the kernel can't analyze your program and know what it's going to do maybe, right? But yeah, that is a good question, but that's why it has to close its own right end because then it negates that possibility. Cool. Cool. All right, so we do not have that much time, but we will do an exam style question. We can follow it up on the Discord if you want, or see it on the other. But quickly, so people love asking these in exams. So for each program, state whether it will produce the same output each time it is run, or whether it produces different outputs when it's run multiple times. So that means if I run it once, will it behave the exact same way if I run it again? So this thing looks scary because there is a while loop with a fork. And last time I showed you a while loop with a fork, it was a fork bomb and it went on forever. Thankfully, this one has some limits. So, to start arguing about this one, well, we can create a process 100 that is created for us that starts executing main. So, in main, this process declares a variable called I and sets it to something like 4. So, it would then check this while loop. Does I equal 0? Nah. So I is not equal to 0, it's going to fork. So that is going to create a new process. I will call it 101 because I'm super creative. So at the top, I will put the parent-child relationships. So parent 100 is the parent of 101. So 101 is going to be a copy of process 100 at the time of the fork. So in 101, do I have a variable called I? Yes, what's it equal to? 4. All right, which one is going to execute? Which one is my kernel going to execute? Process 101 or 100?
Either of them?
Either of them, have no idea. So I'll pick 100, for example. So in process 100, what did it return from fork?
Sorry?
What?
For which process?
Process 100, what did fork return? 101. So it creates a variable called PID, assigns it to 101. It would go into this else, print off whatever 4 is. So it would print, I'll put it in black, it would print 4, and then it would exit 0. So it's now done. So so that process is done. Now we have no other choice but to run 101. So what did 101 return from fork? 0. So 101 would create PID. It would be equal to 0. It would check it with 0. Is 0 equal to 0? Hopefully on this planet. So it would subtract 1 from I. So I would go from 4 to 3. And then it would go here to the while. So that PID variable goes out of scope. So we can delete it. So now, does I equal 0? No. So we go into the loop. We go ahead and we create a new process. Again, this is why I don't get to name children. So I'll call it 102. Thankfully, I don't have to give it a name. Is it going to have a variable called I? Sure. What's it going to be equal to? 3. And at the top, 101 created 102. So now, which one's going to run? I have no idea. Let's say 102 runs. Well, 102, fork would return 0. So PID would be 0. So it would subtract 1 from I, and 3 would go to 2. So because I did this, I subtracted 1 from I. Should I do this as well?
No.
Why?
Because they're independent.
Yeah, they're different processes. You can't affect memory like that on a different process. They're independent. So that wouldn't happen. So 102 would go. PID would go out of scope. It would fork again. Eventually creates 103. We don't really have time. Eventually this thing is going to go, so the tricky part is when it creates 104, in 104, it will decrement, I will become 0, and then in 104, in this while loop, it's not going to execute, it's going to fall through, and it's going to hit this return. Returning from main is the same as exiting, so 104 is just going to die. And then as a spoiler, this process prints 3, 2, and 1, and you don't know what order they're going to print in. So
they're not the same.
yeah, so each time you run this, you might get a different order. So you might get 4, 3, 2, 1. If you get unlucky, you might get 1, 3, 4, whatever I didn't say. Or you might get 3, 2, 1, 4. All right, the order's not specified.
Quick question.
Yeah,
How many points deducted if I mention 0 in the output?
I don't know.
Sure.
Some. So yeah, the next question is, hey, it just throws wait PID into it. And guess what? If you throw a wait PID before the print, it will always print 1, 2, 3, 4. And we can leave that for Discord and stuff like that. So just remember, pulling for you.